Welcome back, physicists. We are going to talk about some more two-dimensional motion problems. Today, what we're really going to focus on is being able to find the position. Oh, no, I didn't want to move that. Why do my pens never work, you guys? I wish I knew. I wish someone could just be like, hey, Mr. Barton, here's why your pens don't work. But we're going to focus on finding the position, not so much the velocity, but we'll talk about it. It'll come up. Of the object at any point in time while an object is moving in two dimensions at once. So before, we just looked at vectors and how to decompose them into x and y pieces. Now what we're going to do is we're going to actually do a few physics problems that have an object moving horizontally and vertically, or in some cases just in two perpendicular directions. There's not really necessarily a horizontal and vertical. It could be two different horizontal directions. It's whatever. As long as it's not moving in a, I guess perfectly, it can move a perfectly straight line, but maybe those lines don't necessarily line up with an obvious set of axes for the system. And you'll see what I mean on the last one. So let me start by giving you a little bit of advice and reminding you of a few things that you probably want to know. Just so that you don't get like too overwhelmed, right? Sometimes you're gonna have an easy problem that has an easy answer, and you're gonna think way too hard about it. So I'm gonna try and help you avoid that with these pro tips. So some pro tips for two-dimensional motion. If you have a choice, start with the simpler direction. So like if you have something moving constant velocity this way. Oh, why is my pen so fat? Let's skinny that up. And then you have something accelerating that way, right? I would look at the constant velocity section first, if I can, and then move on to the piece that's accelerating. But that's not always going to work. But it's a good place to start, right? Always draw a picture. You're going to notice on all three example problems I have for you today, I've already drawn pictures. I think this helps particularly when things are moving in two dimensions at once, because it helps you keep things straight, keep the directions organized, and give you a clear idea of what's going on. If you try and just beat it to death with math, sometimes it's easy to get lost in the sauce and like, what does this label mean again? What direction was that thing again? You know what I mean? If you draw a picture of what's happening, A, you get to draw pretty pictures, which is always a plus. B, it'll help you visualize and understand how to set things up. Okay. Then before you start plugging in numbers, pick some relevant equations. The ones we're going to really focus on today are going to be our displacement equation, which is this thing that I'm writing down right now. And we're going to need to make sure we don't forget the squared on the t. I always forget that. And then maybe we have to dabble a little bit in our velocity equation as well. I don't have any force problems for you yet, just because force problems can get a little tricky, and you want to be able to do two-dimensional motion problems before you start trying to deduce the motion from forces, right? We'll start with like 2 or 3 step problems, and then we'll plug in forces and we'll get 3 or 4 step problems and make them a little more complicated. So we're trying to just avoid an extra step than what's necessary for right now. Okay. Usually with 2D motion problems, you're going to be solving for a variable in one direction, right? The reason they're 2D motion is because you have to look at both directions at once. If you can completely ignore one direction, please do so. But usually with 2D motion problems, you have to use information about one direction and then plug that information back in for the other direction. Meaning you have to look at like your x equation, figure out how long something takes, then plug that into your y equation to figure out how high something goes. All right. Here's some information that we've learned units ago in the one-dimensional motion that I just want to remind you of before we get into problems. So if an object is in free fall, the acceleration is 10 meters per second down towards the ground. Okay. If it's in free fall, remember that means that we are only applying the force of gravity to it. And I know we're not talking about forces, but we can ask ourselves what forces seem like they might apply in this scenario. So again, free fall is anytime you only have gravity on something. An object is in free fall. If an object is in free fall, the acceleration in the x direction is 0. And this is kind of assuming you're using regular x and y, like x is horizontal, y is up and down. But if something is falling and it doesn't have something to push it sideways, like a rocket booster or a hang glider or a big fan or a crosswind, then it's not going to accelerate in the x direction. That's kind of what free fall means. So our acceleration in the x direction will equal 0, which is going to be handy in some of these problems. The last thing is that the x and y direction are independent of each other. So if you're going 5 meters per second in the x direction, and then I say something gives you a hard shove in the y direction, that's not going to change what you're doing in the x direction. You're going to keep doing that thing in the x direction. Now you're just going to gain some y direction speed. So you'll have a new, bigger total velocity, right? And we can use Pythagorean's theorem to solve that if we need to. So here's the relevant ideas. Here's kind of the strategies we're going to try and use. But I have 3 example problems for you today that I think are going to help you see how to set up problems, see what I mean by solve in one direction, then plug in for the other direction. And hopefully they're a little bit of fun. So let's dive into those problems. So we have an airplane that's dropping supplies in a small country, suffering from a lack of healthy snacks. Right? Their parents don't buy them celery and little carrot sticks with some like vinaigrette. Their parents only buy them Takis and hot Cheetos and Doritos and soda. So we've decided that we're gonna pull together and get them some celery sticks and little carrots. So the plane is cruising at a constant 500 meters above the ground. This constant is pretty important here. And is moving at 150 meters per second. This is about 300 something miles an hour, like 330 maybe, 320. The plane releases a reinforced crate with fresh veggies, rice, and clean drinking water. How far horizontally will the package drift before landing on the ground? Assume the package is very aero and there is negligible air resistance. So I'm going to cop out and ignore air resistance because it's too hard and I don't want to think about it, especially if we're going to use real numbers. So let's go ahead and look at this picture. So we have our airplane and it's cruising 500 meters above the ground. So let's maybe indicate that, right? Here's the ground. This height right here, we'll say height equals 500 meters. Okay. And actually, maybe I don't want to use height. Height is a good variable to use in like math and stuff. But physics, we really want to make sure we're keeping y's and x's separate. So I'm going to use y here. So our y is 500 meters. They also tell us that it's at a constant height. So this thing is cruising perfectly horizontal and it's moving at 150 meters per second. So that can be our velocity initial. Velocity initial equals 150 meters per second. And this velocity, I'm going to say this is the x direction, the positive x direction. And we'll make this the positive y direction. So this velocity is 100% in the x direction because we're at a constant height. We're not moving up or down. So our velocity up and down is 0. So what I'm going to do is I'm going to put a little x here to tell me that that velocity is the x initial velocity. So the plane is going to release our crate, this crate right here, and it's going to fall down to the ground. So now let me ask you something. Do you think that our crate is going to fall? Let me get a prettier color. If this plane is going 150 meters per second and it releases the crate, does the crate just drop straight down? What do you think? Like, think about that. Do you think it just drops straight down? Like, you let go of the crate, the plane the plane lost part of its wing. Let me connect that. Sorry. There. Group that up. Okay. The plane keeps moving. Does this box not continue with the plane and just falls straight down? Or what do you think makes sense, right? These are things you're going to have to start asking yourself when you're doing these problems, because it's not just going to tell you. So maybe think about it if you're in a car, right? If you are sitting in a car and you have something in your hand and then you let go, does it stop moving or does it fall straight down into your hand while you're in the car? Well, it'll fall straight down and just hit like your lap or whatever in the car. Your lap is also going 45 miles an hour. So that little box in the car with you is going 45 miles an hour. So our box here has an initial x velocity. The box is moving at 150 meters per second in the x direction. So when our box is released from our plane, it's going to continue to move in the x direction, but then it's going to start to fall. So it's going to fall like that probably, right? So it'll keep moving forward. It won't just land directly wherever it's released. It's going to fall and travel some horizontal distance. And that's actually what we're looking for. How far horizontally will the package drift before landing on the ground? We're looking for this distance here. This x displacement from the x position where it's dropped from straight down to where the box is actually going to land. So we're looking, what is this drift distance here? Okay. So what we want to do is we want to solve for a distance. So it makes sense to me that we should start by looking at a distance equation. So let's grab nice green. And let's talk about our displacement in the x direction. So we have x final equals x initial plus velocity initial in the x direction plus 1/2 acceleration times time squared. And the acceleration is also in the x direction, right? All of these vectors, position or displacement, velocity, and acceleration, they all have x and y components. Some of those components might be 0, but they're all vectors, and we need to talk about them in an x and a y direction. So it doesn't really give us a starting point, right? It doesn't say the plane is over this thing, then it releases the box. It just says it drops the box, how far does it go? So I'm going to go ahead and say that our initial displacement is 0, and just wherever it's like go from, this is x equals 0. And then we want to know x final, this position right here. Our initial, whoops, we should have a t in there. Our initial velocity in the x direction is this 150 right there. And our acceleration, let's go back. An object is in, if an object is in free fall, the acceleration in the x direction is 0. When I just let go of this box, and there's no rockets, no parachute, no nothing, that's in free fall, right? So there's no unbalanced force that will make this box accelerate horizontally. There's nothing pushing it back or pushing it forward. So our acceleration is 0. So our x displacement equation simplifies a lot. Our final x position equals our velocity in the x position, or in the x direction, times time. Okay, that looks good to me. We know this velocity, x final equals 150. We don't know time though, and that's the issue. So if we look at, let's say we're not knowingly in a two-dimensional problem. Let's just look at the velocity equation, right? V final equals V initial plus AT. Acceleration 0. So V initial equals V final, and we can't solve for time there. So this is not going to get us there. So this is why it being a two-dimensional problem is both beneficial and makes it possible for us to solve this. We have information about the y direction. So it says the plane releases. Releases means it doesn't push it down. It doesn't like give it a little shove up. It doesn't toss it up and then let it fall. It just lets go. And then it falls. It's also 500 meters above the ground. So we have some information, and we could write a displacement equation in the y direction. So when I'm talking about the y direction, instead of using x final, x initial, I like to do y's. So y final equals y initial plus velocity initial in the y direction times time plus 1/2 acceleration times time squared. All right. So our initial height, our box is 500 meters above the ground. When it hits the ground, it's on the ground. So this would be y equals 0, y equals 500. So we know the initial and the final position of our box. Velocity, we just talked about how it's being released. So released implies that it has no velocity initially. And it's in free fall. So we know that our acceleration is going to be 10, and we're going to make it negative because it's going to accelerate that way. Because if we look at the force diagram for the box, the only force on this box is weight. So that our unbalanced force is pulling downwards. We're going to accelerate in the downward direction. So we're going to make this negative because we've said up is positive and to the right is positive. So we can use this position equation in the y direction to solve for our time, and then we can go back and plug that time into our x position equation here to solve for our distance in the x direction. So let's go ahead and do that. Y final is 0. Y initial is 500. This term is 0 because it has 0 initial velocity and was released. Minus 1/2 times 10 is 5 t squared. So we subtract the 500 over. We have negative 500 equals negative 5 t squared. Divide by 5. So we have 100 equals t squared. The negatives cancel, of course. We take a square root. So we get t equals 10 seconds. The math aficionados among you will know that when you take a square root, typically you get a positive and a negative time. But in physics, usually we throw away the negative answer because we're saying, after I release this, what happened? After implies that time has gone forward and moved positively. These equations aren't really applicable before it's released because the box wasn't moving. It was something else was happening. The conditions have changed. So now we're going to just plug this in here. And that's very easy for us. So x final equals 150 meters per second times our 10 seconds for time. So our x final will be 1,500 meters from where it's released. So this drift distance here is 1,500 meters, or over a kilometer. So this plane flying at a normal plane speed, if you drop it from 500 feet, the box will go over 1.5 or about 1.5 kilometers before it pretty interesting, pretty fun. I like these. These are fun. They let you really flex your math muscles, and they lend themselves to pretty pictures. They're pretty fun. I like them. All right. Now this is not a true story. This actually, I used to do this as a lab activity. It's more like a practicum. Is an excuse to go outside and throw eggs at your teacher. But I tried to write another problem that was a true story about bullying in high school. But I couldn't make the physics problem work out nicely, so we'll do this other one. So it says, after Mr. Barton's first day of high school, while he was walking out of his last class of the day, another student dropped an egg on him from the second floor of the building. The egg was released from 6 meters above Mr. Barton's head, and Mr. Barton walks with a constant velocity of 1.5 meters per second. And don't ask me how I know that. Actually, go ahead. Ask me. Mr. Barton, how do you know that? Thank you for asking. In college, we did a lab, and we had to measure how fast we walked. And I had the most consistent walk in my lab group. I was so proud. I called my mom. I said, "Mom, you raised such a consistent walker." It was probably one of my proudest days ever. How many seconds before Mr. Barton was directly under the bully did the bully let go of the egg? So let's talk about this problem. Let's talk about the real life situation and try and understand what's happening. Then we'll do the physics. So the bully is up here. This is the bully. Sorry about that. The bully's up here. This is me, the Mr. Barton. And the bully's going to drop this beautifully drawn egg onto my head. So, if the bully, being a dumb bully, waits till I'm directly under the egg, he drops the egg, or she, could have been a girl, I have no idea who did it. Egg goes down, I walk forward. Egg goes down, whoops. Egg goes down some more, I walk some more forward. Egg goes down some more, I walk some more forward. Egg hits the ground, missing me. So, clearly, what the bully has to do is drop the egg before I'm under it. Egg falls, I walk forward. Egg falls, I walk forward. Egg falls, I walk forward. Bada bing, bada boom, I've got egg on my head. So, this is a pretty fun lab activity that you're not going to get to do, but maybe someday. Maybe if I get to 200 subscribers. So what we want to know is how soon or how long, how much time, how many seconds before I'm directly under the bully did the bully need to let go of the egg to hit me? Because if I'm right under, it's not going to hit. So we have to work backwards a little bit. So what we need to do is set up some physics equations. Okay. So there are two things here, right? There's the egg, and then there's me. We need to find the situation that puts my location at the same location as the egg. They have to be equal to each other, right? And now there's a couple of like nuanced things that we might have had to do in a lab, but we're gonna just kind of hand wave it here. So let's reread the question, get some information, shall we? Mr. Barton had a terrible childhood. He was bullied his whole life. That's what made him a physics teacher. The egg was released from 6 meters above Mr. Barton's head. Okay. So normally you have to measure a height and then measure the height of me, and there's a bunch of stuff, but I'm going to just simplify it. This distance from the egg's release to where my head will be, this distance is 6 meters. We already did the math. It's 6 meters. My velocity here is 1.5 meters per second. And what we want is x egg to equal x Barton. We'll just put BA because I'm just B for Barton. Y egg equals y Barton. Okay, so let's go maybe set up some physics equations, right? Let's start with looking at this egg, and then we'll look at me. So for the egg is moving purely in the y direction. So for the egg, we have y egg. Now, let's not even do that. We know we're talking about the egg because it's the only thing moving in the y direction. Y final equals y initial plus velocity initial in the y direction times time plus 1/2 acceleration times time squared. Okay. For our egg, final will be 0, right? Here's y equals 0. Here's y equals 6. Our final will be 6. Our final will be 0. Our initial will be 6. So 0 equals 6. The initial velocity, they're going to just drop the egg. You could make this a little bit more efficient by literally just yeeting the heck out of that egg straight down, but that kind of, you lose some of the stealth, right? If you shout yeet to get the oomph necessary to toss the egg, you lose the element of surprise, right? So you lose the ability to hit unsuspecting victims. It's funnier if they just get hit with an egg. So initial velocity will be 0. This egg is in free fall, so our acceleration once again will be -10. Just because if this is 0 and this is +6, we've kind of implied that up is positive y, and we'll just make to the right positive x again. So we have -5t squared. Okay, it looks like we can figure out how much time it takes for this egg to drop. Okay, it kind of looks like I may have miswritten this question. Let's solve for the time. Subtract the 6, -6 equals -5t squared. Divide by 5, we have 1.2 equals t squared. And then we take a square root on our calculator that has been prepared ahead of time. So t equals 1.0, we'll say 95 seconds. Okay. If you have to measure the egg to more than a thousandth of a second, you're probably in trouble anyway. So there you go. That's actually the time. That's what the question is asking for. How many seconds before Mr. Barn is directly under the bully did they have to drop the egg? We found that. The egg takes 1.095 seconds to fall to the height of my head, so you have to let go of it 1.095 seconds early. Unfortunately, that's kind of hard to do, right? How do you understand how many seconds away I am? It would be much easier to just figure out how far away I would be. So let's go ahead and figure out what the distance from directly under the bully I would have to be. Let's see. Maybe the bully puts like a little mark on the ground. I go, what's that mark? And when you walk over the mark, that's the signal to the bully to drop the egg so that I end up there when the egg hits, right? So let's figure out what is this distance right here. How far away from the bully should I be before they drop the egg? So let's look at the x direction for me. X final equals x initial plus velocity initial in the x direction times time plus 1/2 at squared. All right, acceleration, I walk at a constant velocity, so that's 0. My velocity is 1.5. And time is going to be this time that we just calculated. What we want to know is this position here, this x initial. X final, we can just say wherever this is 0. So what we're going to get here is a negative value for x because I am to the left of where I said 0 is. But that just means I'm that far before under the bully. Does that make sense to you? If not, you should let me know in the WebEx. But the reason it's negative is simply because I'll be on the left side of where I said 0 is. So we're looking for this initial position. So let's go ahead and plug in our numbers. 0 equals x initial plus 1.5 times 1.095. So then we'll just multiply these, and then we will move them to the other side. So we get 0 equals x naught plus 1.643, rounding. Subtract that over. X initial equals negative 1.643 meters. So I need to be 1.643 meters to the left or before where the bully is. Hypothetically, if I were over here, right, and I could be going that way. It doesn't really matter. But I need to be this far from underneath the bully before they drop the egg. So if you want to pull a similar prank, please don't, right? But if you do, one good way to do it is mark a spot on the ground, and then when they walk over this, just let go of the egg, and then you'll nail them right in the head. Fun problem. I like this one. All right. Last one. This is a physics class, so of course we've got to do some stuff in space. So let's do a space problem. So it says a spaceship was on a direct course with a space station before it was hit by an asteroid. The asteroid hit the side of the ship, disabling the engine, and now the ship is drifting at a constant speed of 500 meters per second, 5 degrees off its original course. The spaceship was 2,000 kilometers from the space station at the time of impact. How long will it take before the ship passes the station? How far from the station will the ship be when it passes by? So let's break this up. We have our beautiful spaceship right here. We have our beautiful space station right here. Our ship was on a direct course to the space station. Then it got nailed by an asteroid, and now it is at an angle to that station. It's drifting like this. And this angle is actually probably too big, but we'll roll with it. This angle right here, that's 5 degrees. So we are going 5 degrees from where we were like kind of off track from our space station. The space station is 2,000 kilometers away. So let's mark some stuff up. This distance is 2,000 kilometers. Okay. This is given to us in meters per second. So we should probably turn this into meters. So 1 kilometer is 1,000 meters. So we'll just multiply by 1,000. So we'll add 3 more zeros. We're 2 million meters away. Okay, not too bad. Also, it says we're going at 500 meters per second, but that's at an angle of 5 degrees. So our velocity is going this direction, and I'm going to exaggerate these angles a little bit. This has an x and a y component to the velocity. Here's velocity in the x, here's velocity in the y, here's velocity. All right, so now we need to figure out a few things. How long will it take before the spaceship passes the station? So we want to know, when is our spaceship going to be right here? And then we want to know how far from the station. So what is this distance from the, or maybe y, the way I've drawn the triangle below. How far away from the station will it be when it's passing it? So let's go ahead and try and break this down. If we want to know how long it takes before the ship passes the station, we know a distance. It's going at a constant speed or constant velocity because its engine's been blown out. So we can use the velocity and the angle and the distance to hopefully figure out how far it is from the station. So let's find this distance right here. right? Oh, actually, I'm sorry. We know that distance is 2 million. Let's figure out how long it's going to take this ship to cover that 2 million meters of distance. We can't just divide by 500 because the 500 is at an angle, and not all of our 500 meters per second are progressing us towards the station. Some of it is making us drift sideways. So we need to figure out what is the x component that's going to make us move towards our space station. So we're going to do a little bit of trigonometry. All right, so we know this angle. This side compared to the angle we know, this is the adjacent side. This is our hypotenuse. So we need to think to ourselves, which trig operation uses adjacent and hypotenuse? That's cosine. So we have cosine of our angle equals adjacent, which is velocity in the x direction, divided by our hypotenuse, which is the velocity, 500. Now we're going to multiply both sides by the 500, and then we're going to plug the cosine of 5 degrees into our calculator and multiply by 500 to figure out our x. Because we are only slightly off course, we're expecting this to be very, very close to 500. So if we get something like 200, we probably want to go back and check that our calculator is in degrees and not radians or something weird like that. So our velocity in the x direction is 498.097. And that's it, as close as my calculator says. So let's go ahead and just round that to 498.1. Let's just go ahead and get the y direction. Since we're out here doing trigonometry anyway, this is the opposite side. And again, don't use this rounded number. Even this number is a little bit rounded because of your calculator. Use the number you know. So opposite and hypotenuse, that would be sine of 5 degrees equals v naught y over our hypotenuse times 500. 500 times the sine of 5. This one's going to be much lower because we're barely off course. We're barely drifting in that direction. So when we solve for it, v naught y, we get 43.6 rounding meters per second. Okay, so we have our x and our y velocities. Now, this is our x direction. Let's just say that's our y direction. Let's make down the way I've drawn it. Let's make that the positive y. That way we can leave this positive. So let's look at our position equation in the x direction and see if we have enough information to solve for the time. So position in the x direction equals our initial x plus velocity naught in the x times time plus 1/2 acceleration times t squared. Our initial displacement is 0. Our acceleration, our engines are blown out. We have no unbalanced forces. We're drifting through space. So this is not too bad. X final is 2 million because that's how far our space station is. And then that equals our velocity in the x direction, which is 498.1 times t. So all we have to do is divide 2 million by this velocity, and then that will tell us how far, or rather how long it will take us to return to our space station. So t equals 4,015.26 seconds. The 0.26 is probably not super important, but if you're in space, you know, this is probably life or death. So just to give us some context, that's a little bit over an hour. Let's see, let me check. It's 1.1 hours, so it's about an hour and 6 minutes. Not terrible. An hour and 6 minutes of just chilling. You could probably listen to your favorite CD in that time. All right, so we figured out how long will it take before the ship is passing the station. Now we need to figure out how far from the station. What is this y distance here? How far are the people on the station going to have to go to get us? So now let's look at our displacement in the y direction. Y final equals y initial plus velocity not in the y direction times time plus 1/2 acceleration times time squared. Why not? Here we're dead on, right? Right now, this where we are is y equals 0, and we want to know what y equals over here. Okay, so our initial y position will be 0. We're still drifting, so acceleration in the y direction is also 0. We know our velocity, it's 43.6, and we know our time, it's 4015.26. So we can just multiply those to get our drift, or how far we've gone from the station. So y final equals 43.6 times 4015.26. And then we just throw that in our calculator. 4015.26 times 43.6. And we will go y final equals 175 meters. So just 150 kilometers away. That's about from here to Flagstaff, from Phoenix to Flagstaff. Not that far. So there's not that far. They'll be fine. I'm sure they'll find us. Don't worry, your life's not in danger. So there are some fun problems for you. Hopefully this was not too overwhelming. I tried to keep them pretty simple. And hopefully this helps with your homework. If you're stuck or you're bamboozled by the homework, please ask for help. I know you guys are honors, and it's like, Mr. Barton asked me if I needed some help, and then I took that personally because that's like an affront to your honor. And like, I basically called your mom a bad name or something. It's like, how dare you imply I need help? I can figure this out on my own. But it's my job to help. So if you get tired of beating your head against your table trying to figure stuff out, just ask for help. I promise I will. All right. Have a great day, ladies and gentlemen. Make sure you like and subscribe. I forget what I said I'd do at 200, but I'll do it. I swear I will. Please subscribe.